Look up at the night sky on a clear evening, and you'll see countless stars shimmering like distant diamonds. But what if I told you some of those stars aren't just randomly scattered? They're part of vast, mysterious families called star clusters, cosmic gatherings that hold secrets far stranger than anything we've imagined. These clusters aren't just beautiful, they're time capsules, laboratories, and cosmic puzzles all rolled into one. And the more we learn about them, the more they shake the very foundations of what we thought we knew about the universe. Take the Pleiades, for example, a cluster so bright and close, you can spot it with your naked eye. Ancient cultures worshipped it, poets wrote about it, and for centuries we assumed it was just a pretty grouping of stars. But modern astronomy has revealed something astonishing. The Pleiades is home to stars that shouldn't exist. Some of them spin at impossible speeds, others defy the laws of physics as we understand them, and a few might even be hiding dark matter in ways we never predicted. And that's just one cluster out of thousands. Every time we point our telescopes at these stellar communities, we uncover something new, something bizarre, something that leaves scientists scratching their heads. That's exactly what we're diving into today, 30 of the most mind-bending discoveries about star clusters that'll make you question everything. From rogue black holes lurking where they shouldn't be, to stars that appear older than the universe itself, these findings aren't just curiosities, they're clues to a bigger cosmic story. So buckle up, because we're about to explore the weird, the wild, and the downright shocking truths hidden within these glittering islands of stars. By the end, you'll never look at the night sky the same way again. Imagine staring through a telescope at a patch of sky where you swear there was a dense, glittering star cluster just last week, only to find it's now vanished without a trace. This isn't science fiction, it's the mind-bending reality of what astronomers are calling the phantom star cluster. First spotted in 2019 by a team analyzing data from the Gaia Space Observatory, this mysterious group of stars appeared to hover near the Milky Way's outskirts. But when scientists rushed to confirm it with other telescopes, the cluster had simply disappeared. Then, months later, it flickered back into view, only to vanish again. It's like the universe is playing a cosmic game of hide and seek, and we're left scrambling for answers. So what's going on? One leading theory points to gravitational lensing, a phenomenon where the gravity of an invisible, massive object, like a dark matter clump, bends and magnifies light from stars far behind it. This could create the illusion of a tight cluster where none truly exists, a celestial mirage warping our view. But there's a catch: the phantom cluster reappears in the same spot, which lensing shouldn't allow unless some unseen structure is moving in perfect sync with our observations. That's where things get even weirder. Some researchers speculate we might be seeing light bent by a rogue black hole drifting through interstellar space, its immense gravity briefly focusing starlight like a magnifying glass before it moves on. Then there's the data anomaly camp, who argue this could be a glitch, a rare alignment of stars that only looks like a cluster due to quirks in how telescopes record their positions. But here's the twist: follow-up studies found subtle chemical signatures in the phantom stars that suggest they are genuinely linked, as if they were born from the same cosmic nursery. That's left astronomers in a tug of war between two impossibilities. Either our tools are lying to us in ways we don't understand, or the universe is hiding an entirely new kind of astrophysical phenomenon. Either way, the phantom cluster is forcing us to confront just how much we don't know about the cosmos, and how even the simplest glimmer of light might rewrite the rules. Deep in the heart of the globular cluster Messier 80, astronomers recently stumbled upon something extraordinary: stars that seem to be singing. Not with literal voices, of course, but with rhythmic pulses of radio waves so precise they could be mistaken for a cosmic symphony. These signals, detected by some of the world's most sensitive radio telescopes, arrive like clockwork, pulsing with an eerie regularity that defies conventional explanations. It's as if the cluster itself is humming a tune, and scientists are scrambling to decipher the sheet music. At first, researchers assumed they were dealing with pulsars, the ultra-dense remnants of dead stars that emit beams of radiation like celestial lighthouses. But here's the twist: the signals from Messier 80 don't match any known pulsar behavior. They're too synchronized, too clean, almost as if something or someone is orchestrating them. One theory suggests we might be witnessing a never-before-seen interaction between neutron stars, where their immensely powerful magnetic fields lock into a bizarre resonance, creating these rhythmic bursts. Others speculate about exotic objects like quark stars, hypothetical stellar remnants even denser than neutron stars, whose vibrations could produce such precise frequencies. Then there's the wild card: what if these signals aren't coming from stars at all? Some astronomers have floated the idea of artificial origins, not in the alien megastructure sense, but as naturally occurring lenses of plasma or dark matter that focus and modulate radio waves into these strange patterns. Picture a celestial amplifier taking the chaotic noise of the cosmos and turning it into something melodic. The most tantalizing clue: the signals seem to shift slightly over time, almost like a song changing key. That's led to speculation that Messier 80 might be hiding a dynamic, unseen force, perhaps an intermediate mass black hole at its core, subtly warping space-time and altering the signals as they travel outward. Whatever the cause, these singing stars are more than a curiosity. They're a reminder that even in the oldest, most studied corners of the universe, the cosmos still has the power to surprise us with its mysteries. Westerlund 1 isn't your average star cluster. It's a cosmic demolition derby where stellar giants live fast, die young, and leave behind some of the most bizarre corpses in the universe. Nestled about 15,000 light-years away, this relatively young cluster, just 5 million years old, should theoretically be bursting with massive, luminous stars. But when astronomers trained their telescopes on it, they found something far more unsettling: a swarm of black holes, far more than anyone predicted. This isn't just a cluster, it's a black hole nursery, rewriting our understanding of how these gravitational monsters come into existence. What makes Westerlund 1 so extraordinary is the sheer density of its dark residents. Current estimates suggest there could be hundreds of black holes packed into a region just a few light-years across, like finding an entire graveyard of invisible giants crammed into your backyard. That's wildly out of proportion with traditional models, which assume only 1 or 2 black holes should form in a cluster this size. So why the overcrowding? The answer might lie in the cluster's extreme environment. Westerlund 1 stars are born bigger, burn brighter, and explode sooner than anywhere else we've studied. When these titanic stars collapse, they don't just leave behind typical black holes. They might be creating a new class of compact objects, ones that defy the mass limits we thought were unbreakable. Here's where things get really strange. Some of these black holes appear to be kicking around like cosmic pinballs, flung into chaotic orbits by violent supernova explosions. Normally, such kicks would eject black holes entirely from their home clusters, but Westerlund 1's gravity is so intense and its black holes so numerous that many get trapped in a gravitational dance, orbiting one another in tight, unstable pairs. That's led to an even wilder possibility. This cluster could be a factory for merging black holes, the kind that create ripples in spacetime detectable by observatories like LIGO. If true, it means we've been underestimating how often these cosmic collisions occur and where they originate. The implications are staggering. If Westerlund 1 isn't unique, there could be thousands of similar clusters peppered throughout the galaxy, each churning out black holes at a rate that upends our textbooks. It challenges the long-held assumption that black holes are rare relics of isolated stellar deaths. Instead, they might be social creatures, born in frenzied stellar metropolises where gravity reigns supreme. For theorists, this raises thorny new questions. Could these clusters seed supermassive black holes by merging their smaller counterparts? Are we looking at the birthplace of the universe's most destructive objects? Every new observation from Westerland 1 blurs the line between science and science fiction, proving once again that when it comes to the cosmos, the truth is often stranger than anything we could invent. Hidden within the ancient globular cluster NGC 6397, astronomers found a celestial treasure trove that could rewrite what we know about stellar afterlife. These aren't ordinary white dwarfs, the dense, Earth-sized cores left behind when stars like our Sun exhaust their fuel. These are cosmic diamonds on a scale beyond human imagination, their carbon-rich atmospheres slowly crystallizing into structures that might resemble planet-sized gemstones. But here's the catch: according to everything we thought we knew about stellar evolution, they shouldn't exist in this cluster at all. The mystery starts with the cluster's age. NGC 6397 is one of the oldest known globular clusters, estimated to be nearly 13.5 billion years old, almost as ancient as the universe itself. Conventional models predict its white dwarfs should have cooled into dark, inert husks by now, their atmospheres dominated by helium or hydrogen after billions of years of fading. Yet when researchers analyzed their light spectra, they found something astonishing: a population of white dwarfs gleaming with carbon atmospheres like cosmic embers refusing to fade. Even stranger, these stars show signs of crystallizing, their interiors solidifying into crystalline lattices of carbon and oxygen, a process analogous to diamond formation but on a stellar scale. So how did these diamond dwarfs defy the rules? One theory suggests they're the product of epic stellar collisions. In the cluster's crowded core, stars might have smashed together long ago, stripping away their outer layers and exposing carbon-rich interiors that would normally remain hidden. Another possibility involves chemical peculiarities in the cluster's primordial gas, which could have birthed stars with unusual compositions from the start. But the real bombshell is what this means for cosmic timelines. If these white dwarfs are crystallizing faster than expected, it implies they cooled far more rapidly than models predict, shaving billions of years off the presumed lifespan of stellar remnants. The implications ripple outward. If white dwarfs in ancient clusters can transform into diamonds faster than we thought, it challenges our ability to use them as cosmic clocks to date the universe. Suddenly, these glittering corpses aren't just curiosities. They're potential proof that our understanding of stellar aging has fundamental gaps. And if their carbon atmospheres are more common than assumed, it raises an even wilder question. Could the universe be littered with diamond-rich stars we've overlooked? For now, NGC 6397 offers a tantalizing glimpse of stellar alchemy at work, where death and beauty collide in ways we're only beginning to comprehend. The Pleiades star cluster has dazzled stargazers for millennia, but hidden among its familiar blue giants lies a population of celestial orphans, rogue planets drifting untethered to any sun. These aren't just rare strays. Infrared surveys reveal dozens, possibly hundreds, of these nomadic worlds lurking between the stars, some so young they still glow with the heat of their formation. Their very existence forces us to confront a cosmic conundrum. Were they violently ejected from their birthplaces, or did they form in the darkness like cosmic castaways? One camp of astronomers argues for a chaotic origin story. Young star systems are turbulent places where gravitational tugs of war between sibling planets can fling the losers into interstellar space. In the Pleiades, where stars are packed tightly, a close encounter with a passing neighbor might have ripped entire planets from their orbits. Supporting this theory, some of these rogue worlds show chemical fingerprints matching the cluster's stars, suggesting they were born in traditional planetary nurseries before being exiled. But there's a twist. Not all these wanderers fit the ejection narrative. A subset appear too massive and too isolated to have been kicked out, leading researchers to propose something radical. they might have formed alone, collapsing directly from gas clouds too small to ignite into stars. Think of them as failed stars that never grew up, or overachieving gas giants that built themselves without a stellar blueprint. The Pleiades' dense gas reservoirs could have provided the perfect nursery for such fringe objects, blurring the line between planets and brown dwarfs. The implications are staggering. If rogue planets can form freely in clusters, they might outnumber star-bound worlds across the galaxy. Some could even host subsurface oceans, kept liquid by gravitational squeezing or radioactive heat, raising the tantalizing possibility of nomadic life adrift between the stars. Meanwhile, their sheer abundance challenges our planet-hunting methods, which traditionally focus on stars. The Pleiades' free-floating fleet reminds us that the universe still holds surprises in its shadows, rewriting the rules of planetary formation one orphaned world at a time. NGC 6791 shouldn't exist, at least not the way we see it. This ancient star cluster, clocking in at nearly 8 billion years old, defies cosmic logic by hosting stars that act like rebellious teenagers. While most clusters its age are filled with fading red giants and cooling white dwarfs, NGC 6791 sparkles with unexpectedly youthful stars, burning bright and blue as if time forgot to touch them. It's like finding a medieval castle where the knights are still polishing their armor and throwing parties. So what's keeping these stars so lively? One theory points to stellar vampirism binary systems where one star siphons fuel from its companion, effectively hitting the cosmic reset button on its lifespan. In the dense heart of the cluster, such close encounters could be common, allowing older stars to steal enough hydrogen to reignite their cores and masquerade as younger versions of themselves. But there's a flaw in this elegant explanation. The cluster's blue stragglers are too numerous and too evenly distributed for random theft to account for them all. That's led astronomers to a wilder idea: delayed evolution. Some stars in NGC 6791 might be born with unusually high levels of helium, a trait that would make them burn slower and cooler for billions of years before suddenly flaring up in a late-stage burst of energy. Picture a candle designed to smolder for decades before erupting into flame, except in this case, the candle is a massive star playing the long game. Supporting this, spectroscopic studies reveal peculiar chemical abundances in these stars, hinting at primordial conditions that set them on a different aging path from birth. Then there's the collision hypothesis. In the cluster's cramped quarters, stars might have merged outright, creating Frankenstein's monsters with fresh fuel reserves and extended lifespans. Computer simulations show these mergers could produce stars that look deceptively young, their outer layers churned and rejuvenated by the violent union. But here's the kicker. If mergers are the primary culprit, NGC 6791 should be littered with the remnants of these cosmic crashes, stellar zombies that refuse to die quietly. Yet we've found no clear evidence of them, leaving the mystery wide open. The implications ripple far beyond one oddball cluster. If stars can cheat time through mergers, theft, or innate quirks, it means our models of stellar evolution might be missing entire chapters. Suddenly, estimating the age of distant galaxies becomes trickier. What if their young stars are actually ancient imposters? Even more tantalizing is the possibility that NGC 6791 isn't unique. There could be countless clusters hiding in plain sight, their true ages obscured by stellar sleight of hand. For now, this cosmic retirement home full of seemingly sprightly stars remains a beautiful enigma, proving once again that the universe loves a good paradox. Globular cluster M15 has long been a favorite among astronomers for its dazzling core, a knot of hundreds of thousands of stars packed so tightly they resemble a celestial beehive. But peer closer and something unsettling emerges. Where are all the red giants? These swollen, aging stars should dominate ancient clusters like M15, their ruby glow as reliable as clockwork in stellar aging. Yet here they're conspicuously scarce, as if the cluster has been quietly purging its elders. This isn't just a quirk, it's a cosmic crime scene, and the evidence points to forces we're only beginning to unravel. One explanation hinges on M15's extreme density. In this stellar mosh pit, stars don't just drift peacefully, they jostle, collide, and sometimes cannibalize one another. Computer simulations suggest red giants here might be getting ripped apart before they can fully mature, their outer layers stripped away by gravitational harassment from neighbors. Picture a fragile balloon tossed into a crowd. It doesn't stand a chance. Supporting this, astronomers have spotted streams of gas swirling through the cluster, possibly the remnants of these stellar shreddings. If true, it means M15 is a brutal retirement home where stars rarely get to grow old gracefully. But there's a competing theory that's even more provocative. Dark matter might be meddling. Most globular clusters are thought to be nearly devoid of dark matter, but M15's motion suggests hidden mass lurking in its core. If present, this invisible material could be warping the very fabric of the cluster, altering how stars evolve. One radical hypothesis proposes that dark matter particles interact with red giants' cores, sapping their energy and causing them to collapse prematurely into white dwarfs, skipping the red giant phase entirely. It's as if something is snuffing out these stars' final act before the curtain rises. Then there's the wild card stellar archaeology. M15 stars have odd chemical fingerprints with shockingly low levels of elements like carbon and oxygen, which red giants typically produce in abundance. This hints that earlier generations of stars might have polluted the cluster's gas in ways that stunted later red giants' growth, like a poisoned well affecting everyone who drinks from it. Whatever the cause, M15 forces us to confront a humbling truth. Even the most predictable stages of stellar life might have loopholes we've yet to imagine. And if these missing red giants aren't just a local anomaly, but a signpost of deeper cosmic rules, it could reshape how we interpret aging stars across the universe. Omega Centauri has always stood out among star clusters. It's so massive, astronomers debate whether it's a cluster at all or the stripped core of an ancient dwarf galaxy. But recent observations have revealed something even stranger threading through its heart. Eerie, dark strands like cosmic cobwebs stretching across its core. These aren't dust lanes or gas clouds as we know them. There's something far more puzzling, structures so dense they blot out starlight entirely, yet they don't behave like any known form of matter. It's as if the cluster is wearing scars from battles we can't yet comprehend. The first clues came from Hubble's sharp-eyed observations. While mapping the cluster's crowded center, astronomers noticed bizarre patches where stars seemed to vanish, not just dim but disappear completely. Zooming in, they found these weren't random voids but intricate filaments, some twisting like ropes, others fanning out like veins. At first, scientists assumed they were seeing wreckage from a cannibalized dwarf galaxy, the kind of debris left when a small galaxy gets torn apart by Omega Centauri's gravity. But the math didn't add up. These strands were too organized, too evenly spaced, as if shaped by forces beyond simple destruction. That's where things took a speculative turn. Some researchers propose these filaments could be the fingerprints of dark matter, not the diffuse halo we usually associate with galaxies, but concentrated rivers of it flowing through the cluster's core. In this scenario, the strands might be cosmic fault lines, places where dark matter's gravitational pull has sculpted normal matter into eerie, thread-like structures. There's precedent for this. Simulations of dark matter interactions sometimes produce similar tendrils, though never on such a visible scale. Then there's the plasma possibility. Omega Centauri's core crackles with magnetic fields, strong enough to trap and twist ionized gas into braided filaments. Imagine a stellar-scale version of the aurora's shimmering curtains, but frozen in place and dense enough to eclipse stars. If true, it would mean the cluster is threaded with a hidden electromagnetic skeleton. invisible to most telescopes yet shaping everything around it. But the most tantalizing theory, these strands might be something entirely new: cosmic strings, hypothetical defects in spacetime itself, left over from the universe's birth. Though purely theoretical until now, such structures would appear exactly like these dark filaments, ultra-dense, invisible to conventional detection, and capable of warping light around them. If confirmed, it would be the first physical evidence of a phenomenon physicists have speculated about for decades. Whatever their origin, these dark strands force us to confront how little we understand about even the closest star clusters. Omega Centauri's shadowy threads aren't just curiosities. They could be signposts to physics beyond our current models, hiding in plain sight among the glittering stars. And that's the real mystery. In a universe where darkness often holds the deepest secrets, what else might we be overlooking? 47 Tucanae should be a serene retirement home for ancient stars, a tightly bound family of stellar elders drifting peacefully through the galaxy. But look closer and you'll find chaos lurking in its heart. Astronomers tracking this globular cluster have spotted something extraordinary: stars catapulting outward at over 1,000 kilometers per second, fast enough to cross the continental United States in under 4 seconds. These aren't just drifting away, they're being flung into the cosmic void like bullets from a celestial gun. The question isn't just how they're achieving these mind-bending speeds, but what monstrous force could possibly kick them out with such violence. One leading suspect is a hidden middleweight black hole, a gravitational monster with the mass of 1,000 suns, lurking unseen in the cluster's core. Picture a cosmic slingshot. As stars swing too close to this invisible predator, its immense gravity could fling them outward at speeds that defy logic. Supporting this theory, the runaway stars all seem to originate from the same central region, as if something massive and unseen is hurling them like a pitcher throwing fastballs. But there's a problem. Despite exhaustive searches, no direct evidence of this black hole has surfaced. Its existence remains a tantalizing what if, leaving astronomers divided. Enter the stellar pinball theory. In 47 Tucanae's densely packed core, stars don't just orbit politely, they ricochet off one another in a high-speed game of gravitational billiards. Computer simulations show that when multiple stars interact in close quarters, the weakest member can get ejected at astonishing speeds, while the others recoil deeper into the cluster. It's like a cosmic version of Newton's cradle, where the energy transfer becomes so extreme it launches stars into the galactic wilderness. Some of these runaways even show chemical scars, abnormal levels of helium or nitrogen, hinting they were torn from binary companions during these violent encounters. But here's where the plot thickens. A handful of these hypervelocity stars are moving too fast for even multi-star interactions to explain. Their trajectories suggest they received an extra boost, possibly from a black hole's gravity assisting in their ejection. This has led to a hybrid hypothesis. Perhaps both mechanisms are at work, with close stellar encounters priming stars for expulsion before a mid-mass black hole delivers the final, devastating kick. The implications stretch far beyond one cluster. If mid-mass black holes are common in globular clusters, they could solve the long-standing mystery of how supermassive black holes form, by merging these smaller counterparts over cosmic time. And if multi-star interactions dominate, it means dense star clusters are far more dynamic and destructive than we imagined, reshaping our understanding of how galaxies evolve. Every hypervelocity star streaking away from 47 Tucanae carries a message. Even in the quietest corners of the universe, there's no such thing as true stillness, only forces waiting to be unleashed. Globular cluster NGC 2808 has long fascinated scientists with its unusually complex stellar population, but recent observations have uncovered something even more perplexing: stars that seem to be starving for oxygen. These celestial oddballs, some of the brightest in the cluster, show oxygen levels up to 10 times lower than expected, as if something, or someone siphoned away this vital element before they formed. This isn't just a quirk, it's a cosmic whodunit that could rewrite how we understand the violent origins of some of the universe's oldest stars. One possible culprit: supernovas with a dark twist. Normally, when massive stars explode, they seed their surroundings with oxygen and other heavy elements, enriching the next generation of stars. But in NGC 2808's case, theorists speculate that a rare breed of supernova, one with such extreme conditions that oxygen gets locked into neutron-rich isotopes or even swallowed by black holes, might have altered the chemical playing field. Picture a stellar explosion so violent it doesn't just scatter elements, but actively destroys them, leaving behind a strange, oxygen-poor gas cloud for future stars to inherit. Supporting this, some of these oxygen-deprived stars also show elevated levels of sodium and aluminum, the telltale byproducts of reactions that occur under these extreme conditions. Then there's the primordial soup theory. NGC 2808 might have formed from a pocket of early universe gas that was bizarrely lopsided, perhaps stretched thin by collisions with other gas clouds or filtered through dark matter structures we don't yet understand. In this scenario, the cluster's first stars would have been born into a chemical environment unlike anything we see today, missing key ingredients from the start. It's like baking a cake with no flour. The end product is fundamentally different, not because of something that happened during baking, but because the recipe was flawed from the outset. The implications ripple far beyond one cluster. If supernovas can selectively erase elements, it means our models of chemical enrichment across the cosmos might be missing critical chapters. Worse, if primordial gas clouds had dead zones where certain elements were scarce, it challenges our ability to use stellar chemistry as a universal clock for dating galaxies. But the most tantalizing possibility, these oxygen-starved stars might be messengers from a time before the universe's elemental palette was fully set, a relic population holding clues to processes we've never witnessed firsthand. Until we solve their mystery, NGC 2808's strange stars will keep whispering secrets we're only beginning to decode. The Beehive cluster has always been a jewel of the night sky, a sparkling swarm of stars so close and bright, it's visible to the naked eye. But hidden among its familiar glow lies a cosmic puzzle, a sharp boundary where stars abruptly vanish, as if an invisible wall slices through the cluster. This isn't just a random drop-off, it's a razor-thin divide between a bustling stellar neighborhood and an eerily empty void, and no one knows what's holding the stars back. At first glance, you'd expect stars to thin out gradually, like a city fading into suburbs, but in the Beehive, it's more like hitting a force field. Telescopes reveal a stark line where stellar density plunges by over 90% within a span smaller than our solar system. Stars on one side crowd together like commuters in a rush-hour train, while the other side lies nearly deserted. Some unseen force is corralling them, and the usual suspects don't quite fit. Gravity alone can't explain such a sharp edge. It's too precise, too abrupt. Could magnetism be the invisible jailer? The Beehive crackles with magnetic activity, and some theorists suggest an extreme field here might trap ionized gas, creating a boundary so dense young stars get trapped inside like fireflies in a jar. Imagine a stellar nursery wrapped in a magnetic fence, its lines of force so tangled they act as a barrier. Supporting this, radio telescopes have detected strange synchrotron emissions near the edge, a telltale sign of high-energy particles spiraling in magnetic fields. But there's a catch. Even the strongest magnetic fields we've modeled shouldn't be able to hold back stars so effectively. That's led to a darker hypothesis, a rogue clump of dark matter drifting through the cluster like an unseen iceberg. If a dense knot of this shadowy material settled here, its gravity could sculpt the starfield into this unnatural border. It wouldn't be visible, but its pull would be undeniable. Intriguingly, the Beehive sits in a region of the Milky Way where dark matter streams are predicted to converge, raising the tantalizing possibility that we're seeing one of these phantom structures at work. Yet the most bizarre explanation comes from an unexpected quarter: stellar feedback. The beehive's brightest stars blast out torrents of radiation and solar wind, which could, in theory, push surrounding gas outward until it forms a shock front, a pressure wave strong enough to halt star formation at its edge. Picture a cosmic version of a sandblaster carving a cliff face, except here the cliff is made of unborn stars. If true, it means the beehive's invisible barrier might not be a wall at all, but a fossilized echo of the cluster's most violent youth. Whatever the cause, this sharp divide challenges our assumptions about how star clusters evolve. If unseen forces can sculpt them with such precision, what other invisible boundaries lurk in plain sight across the cosmos? The beehive's mystery reminds us that even the most familiar patches of sky can hide secrets, and sometimes the universe's quietest edges speak the loudest. In the vast cosmic dance of star clusters, NGC 1850 and NGC 1851 defy the odds. They're separated by hundreds of light years, yet they host stars so chemically identical, it's like finding two distant orchestras playing the same symphony note for note. Normally, star clusters develop unique chemical fingerprints based on their birth environments, shaped by local supernovas, gas clouds, and cosmic accidents. But these two globular clusters break all the rules, their stars matching not just in broad strokes but in eerie, trace element detail. It's as if the universe copied and pasted the same stellar blueprint in two unrelated corners of space. So how did this cosmic coincidence happen? One camp of astronomers argues for a shared origin story. Billions of years ago, these clusters might have been born from the same colossal gas cloud, a fragmented stellar nursery whose pieces drifted apart over eons. Think of it like twins separated at birth, carrying the same genetic code despite growing up in different homes. Supporting this, both clusters orbit the Large Magellanic Cloud, a satellite galaxy of the Milky Way, hinting they could be survivors from a single, ancient structure torn apart by tidal forces. If true, their matched chemistry becomes a celestial breadcrumb trail, pointing back to a lost progenitor we've yet to discover. But there's a twist: their stars aren't just similar, they're virtually interchangeable, down to rare elements like europium and barium. That level of precision goes beyond shared ancestry. It suggests something far stranger. One radical theory proposes these clusters pass through the same chemical filter, perhaps a region of space where an intervening gas cloud or dark matter structure scrubbed their stars clean of certain elements, leaving behind unnaturally pure compositions. Picture two rivers flowing through identical purification systems. Their waters might end up matching even if their sources were different. Then there's the wild card: synchronized evolution. Computer simulations show that if two clusters form under nearly identical conditions, same gas density, same supernova seeding, same initial element mix, their stars could theoretically evolve along parallel paths, converging chemically despite never interacting. It's a cosmic version of convergent evolution, where unrelated species develop similar traits because they faced the same environmental pressures. For NGC 1850 and 1851, that pressure might have been an early universe phenomenon we no longer see today, a lost recipe for star formation that left these clusters as accidental copies. The implications ripple far beyond these two oddballs. If clusters can achieve such perfect chemical twinship, it challenges how we use stellar compositions to trace galactic history. Suddenly, matching element ratios don't guarantee shared origins, they might just mean shared circumstances. Worse, if some unseen process can standardize cluster chemistry, it means the universe might be hiding cosmic forgeries, stellar families that look related but aren't. For now, these twin clusters stand as a reminder that even in the chaos of the cosmos, patterns can emerge, patterns so precise, they force us to question whether we're seeing coincidence or conspiracy. Globular cluster M62 should be a steady beacon in the cosmos, an ancient, predictable gathering of stars whose collective glow has barely wavered over billions of years. But when astronomers began monitoring it with precision instruments, they caught something utterly bizarre. The entire cluster flickers, not subtly, not occasionally, but in dramatic, unpredictable surges and dips that defy every model of stellar behavior. One week it shines 10% brighter, the next it dims like a candle in the wind. This isn't just a minor fluctuation, it's as if something massive and invisible is playing a cosmic game of peekaboo with the cluster's light. Initial suspicions pointed to a swarm of rogue planets or brown dwarfs drifting through M62's core, their transits briefly blocking starlight. But the math never added up. For these dips to occur so frequently and so unevenly, the cluster would need thousands of these dark objects packed into a space just a few light years across, a density so extreme it should have triggered gravitational chaos long ago. Worse, some brightness changes happen too fast for any physical object to explain. It's like watching shadows flit across a wall, but there's nothing casting them. That's when theorists turn to more exotic explanations. One compelling idea involves spacetime itself. If M62 harbors a dense central object, perhaps a black hole or a cluster of neutron stars, their combined gravity could warp the fabric of reality around them, creating lenses that magnify and distort light from background stars. As these lenses shift and ripple, they'd produce erratic brightness changes across the entire cluster. Imagine holding a funhouse mirror up to a chandelier, twist it slightly, and the reflections dance unpredictably. In this case, the mirror is space-time, and the twists come from unseen masses moving through it. Yet even this elegant theory can't fully explain M62's behavior. Some fluctuations occur symmetrically across the cluster, as if an invisible hand is adjusting a universal dimmer switch. This has led to a more radical proposal: dark matter interactions. If certain types of dark matter particles clump densely in the cluster's core, their occasional collisions or decays might release bursts of energy not as light, but as gravitational waves or other exotic radiation that subtly alters how starlight escapes the region. It's a long shot, but if true, M62 could be our first glimpse of dark matter's shadowy fingerprints on the visible universe, the most haunting possibility. We're seeing the cluster through a cosmic veil. Simulations suggest M62 might be drifting through a filament of ionized gas left over from the universe's infancy, a structure so diffuse it's normally invisible but thick enough to subtly refract starlight as the cluster moves. Like sunlight glinting through rippling water, this intergalactic current could be bending M62's light in ways that confuse our telescopes. Whatever the cause, this flickering enigma forces us to confront a humbling truth. Even the most stable-looking corners of the cosmos might be teeming with unseen activity. M62's erratic glow isn't just a curiosity, it's a flashing warning light on the dashboard of astrophysics, signaling that our models of star clusters are missing something fundamental. And until we decode its secrets, every flicker carries the same unnerving question: what else are we not seeing? Somewhere in the outskirts of the Milky Way, a star cluster is dancing with nothing, or at least that's what it looks like. Scientists observing NGC 3216 noticed something profoundly odd. Its stars move in perfect, synchronized orbits around, well, nothing at all. No visible central mass, no supermassive black hole, not even a hint of gas or dust. Just an invisible focal point, an empty stage where gravity's conductor should be standing. This isn't just a missing object, it's a gravitational ghost, pulling the strings of an entire stellar performance without ever showing itself. So what could possibly bend an entire cluster to its will without emitting a single photon? The leading suspect is a dark matter halo, an enormous, invisible sphere of this mysterious material, dense enough to hold the cluster in its grip yet completely transparent to our telescopes. Think of it as the universe's most frustrating game of hide and seek, where the hider leaves footprints but refuses to be seen. Models suggest this halo could weigh as much as 10,000 suns, packed into a region just a few dozen light-years wide. That kind of density would make it one of the most extreme dark matter concentrations ever detected, bending the very fabric of space-time without leaving a trace. But here's where the mystery deepens. Dark matter halos aren't supposed to behave like this. They typically sprawl across entire galaxies, diffuse and wispy, not crammed into tight, cluster-sized knots. If NGC 3216's invisible anchor truly is dark matter, it challenges decades of assumptions about how this enigmatic substance clumps together. Some theorists suggest we might be looking at a rare dark matter minihalo, a leftover fragment from the universe's chaotic infancy that somehow survived intact. Others propose something wilder, that this could be a rogue blob of ultra-dense dark matter, a hypothetical form of the material that behaves more like a liquid than a gas, pooling into dense pockets rather than spreading thin. Then there's the black hole loophole. Could an intermediate mass black hole, too faint to detect directly, be masquerading as dark matter? It's possible, but there's a catch. Even stealthy black holes usually betray their presence through X-rays or gravitational lensing. This void shows none of those signs. Its silence is so complete, it's as if the laws of physics themselves are being rewritten. The implications ripple far beyond one strange cluster. If invisible halos like this are common, they could explain other cosmic anomalies, galaxies that rotate too fast, star clusters that move too erratically, even gravitational wave signals that don't quite match predictions. Worse, it means the universe might be littered with these gravitational mirages, invisible puppeteers tugging on stellar strings without ever taking a bow. For now, NGC 3216's empty heart remains a tantalizing enigma, a reminder that sometimes the most powerful forces in the cosmos are the ones we'll never see. Terzan 5 isn't just another globular cluster, it's a cosmic time bomb, crackling with an eerie glow that shouldn't exist. Nestled near the Milky Way's core, this ancient stellar city harbors stars pumping out gamma rays at energies so extreme they rival the aftermath of supernovas. These aren't your garden-variety stellar light shows, they're violent, unexplained bursts of radiation, as if something inside the cluster is tearing apart the laws of physics and rewriting them in gamma-ray graffiti. The leading suspect, neutron star smash-ups, Terzan 5 is packed with these ultra-dense stellar corpses, some spinning hundreds of times per second, their gravitational pull so intense they warp spacetime itself. When two of these frenzied objects spiral into each other, the collision doesn't just produce gravitational waves, it could unleash a firestorm of gamma radiation, lighting up the cluster like a cosmic strobe. But there's a problem. The gamma rays we're seeing don't match the expected signatures of neutron star mergers. They're too frequent, too evenly spaced, almost as if something is triggering them on a schedule. That's where dark matter enters the scene. Some theorists propose that Terzan 5's core might be a dark matter hotspot, where invisible particles collide and annihilate, converting their mass into raw energy. Picture a shadowy fireworks display with dark matter explosions detonating silently in the void. Their only trace the gamma rays that punch through the cluster's heart. If true, it would mean we've accidentally stumbled onto one of the universe's most elusive phenomena, dark matter's destruction playing out in real time. Yet the plot thickens. A handful of Terzan 5 stars exhibit bizarre chemical compositions, laced with heavy elements like gold and platinum that typically form in cataclysmic neutron star collisions. This suggests the cluster might be a factory for cosmic alchemy, where stellar violence forges rare elements and then flings them into space. But here's the twist: these enriched stars aren't clustered near the gamma-ray sources. They're scattered randomly, as if some unseen force, perhaps a rogue intermediate mass black hole, has been stirring the pot. redistributing the cluster's treasures like a cosmic blender. The implications are staggering. If Terzan 5's gamma rays come from dark matter, it could give us our first direct window into this mysterious substance's behavior. If they're from neutron star crashes, it means these collisions are far more common and far stranger than we thought. Either way, this radioactive cluster is forcing us to rethink how stars live, die, and sometimes defy every expectation. One thing's certain, Terzan 5 isn't just shining its screaming secrets into the void, and we're only beginning to listen. Palomar 1 is the cosmic equivalent of a lone tree standing in a hurricane, somehow surviving against all odds. This star cluster shouldn't exist, let alone thrive, in the chaotic wreckage of a galactic collision. Most clusters born in the violent tides of merging galaxies get shredded apart, their stars scattered like dust in the wind. Yet here sits Palomar 1, a young, sparsely populated cluster defiantly holding its ground in the Milky Way's outskirts, where ancient merger debris still lingers. It's a celestial rebel, breaking every rule about where and how star clusters can form and survive. The first red flag, its age. At roughly 6.5 billion years old, Palomar 1 is practically a toddler compared to the ancient globular clusters that dominate our galaxy. But youth alone isn't the issue, it's where it's parked. This cluster orbits through a graveyard of stellar streams, remnants of dwarf galaxies torn apart by the Milky Way's gravity billions of years ago. In this demolition zone, the tidal forces are brutal enough to rip apart even the toughest star clusters. Yet Palomar 1 remains intact, its stars clinging together with a tenacity that baffles theorists. So how does it cheat destruction? One theory suggests it's a cosmic fugitive, a cluster born far from the merger zone that later wandered into this danger-filled neighborhood. If it formed in a quieter region of space, its loose structure might have allowed it to flex and bend under tidal stresses without fully disintegrating. Think of it like a willow tree versus an oak, where rigid clusters snap. Palomar 1's flexibility could let it sway with the gravitational currents. Supporting this, its stars move in unusually elongated orbits, hinting at past close calls with the Milky Way's disruptive forces. But there's a catch. Palomar 1's chemistry doesn't match the Milky Way's native clusters. Its stars have odd ratios of elements like magnesium and iron, signatures that align more closely with the dwarf galaxies the Milky Way has devoured. That's led to a wilder idea. Maybe this cluster isn't a survivor at all, but a resurrected one. Some simulations show that during galaxy collisions, dense pockets of gas can get squeezed hard enough to ignite new star formation, even amid the chaos. Palomar 1 might be a second-generation cluster, born from the ashes of its destroyed predecessors, inheriting their chemical quirks while dodging their fate. Yet the most tantalizing clue lies in what's missing. Palomar 1 has shockingly few red giants for its age, stars that should be plentiful in a cluster this old. This suggests something might be culling its population prematurely, perhaps an unseen mass like a rogue black hole or dark matter clump, lurking in its core, gobbling up stars before they can age. If true, it would mean Palomar 1 isn't just surviving against the odds, it's playing by a completely different rulebook. One thing's certain, this scrappy little cluster is forcing astronomers to rethink how stellar communities endure in the universe's most violent neighborhoods. Whether it's a fugitive, a phoenix, or something stranger, Palomar 1 proves that even in a cosmos ruled by chaos, there's always room for an underdog. Globular clusters are supposed to be celestial beehives, chaotic swarms of stars buzzing in every direction with no discernible pattern. But M53 shatters that expectation with a twist no one saw coming. Its stars are arranged in delicate, sweeping spiral arms, like a miniature galaxy hidden within the cluster's core. This isn't just unusual, it's unprecedented. Spiral structures require ordered motion, a synchronized dance of gravity and rotation that shouldn't exist in the free-for-all of a globular cluster. Yet there they are, etched across M53's heart as clearly as the arms of the Milky Way itself, a cosmic contradiction demanding an explanation. The first clue to this enigma lies in the cluster's unusual rotation. Most globular clusters spin so slowly, their stars move like grains of sand in a barely tilted hourglass, barely influenced by the cluster's overall motion. But M53 whirls with purpose, its core rotating fast enough to impart order to the chaos. Imagine stirring a cup of tea too slow, and the leaves drift randomly, fast enough, and they spiral into the center. Here, gravity's stirring seems to have sculpted the stars into these eerie arms, with older, redder stars concentrated along the crests while younger, bluer ones trail behind like foam on a wave. But rotation alone can't explain the arm's longevity. In a dense cluster, stellar close encounters should shred such fragile structures within millions of years, a blink in cosmic time. That's led astronomers to suspect a hidden architect, perhaps an intermediate mass black hole, its gravity shepherding stars into orderly lanes like an invisible traffic cop. Supporting this, the spirals pitch how tightly its arms coil matches simulations where a central black hole's pull organizes surrounding stars. Yet searches for this black hole have come up empty, leaving the spiral's persistence as baffling as its beauty. Then there's the collision hypothesis. M53 orbits the Milky Way in a region littered with dark matter subhalos, invisible clumps, whose gravity might have jostled the cluster violently enough to trigger spiral formation. Picture tossing a pebble into a pond. The ripples could, in theory, translate to stellar densities if the impact were just right. Some researchers even speculate M53 might be the survivor of a near miss with another cluster, its stars still reeling from the gravitational aftershocks. The most tantalizing possibility: we're witnessing the aftermath of a cosmic heist. Globular clusters often harbor binary stars, and if M53's binaries were systematically broken apart by interactions, their stolen energy could have injected enough motion to spin up the cluster. Like a pinwheel set spinning by scattered gusts, these stellar breakups might have unwittingly sculpted the spiral we see today. Whatever the cause, M53's arms force us to confront how little we understand about the inner lives of star clusters. They're not just static relics of the early universe, they're dynamic, evolving structures capable of surprises that rewrite the rules. And if one cluster can hide a spiral, what other secrets might be lurking in plain sight, waiting for us to look closer? Globular cluster M22 has always stood out from its peers, but not for the reasons you might expect. Tucked away in the constellation Sagittarius, this ancient swarm of stars holds a bizarre secret. It appears to have not one, but two distinct cores, glowing side by side like mismatched eyes in a celestial face. Normally, clusters settle into a single dense heart over billions of years, their stars drawn inward by gravity's relentless pull. Yet here, the rules seem broken, with two bright knots of stars stubbornly refusing to merge. It's as if the universe left a cosmic under construction sign hanging over M22, frozen in time halfway through some mysterious project. At first glance, the most obvious explanation is a past collision. Two separate clusters smashing together but never fully combining, like swirling cream into coffee but stopping before the blend finishes. Computer simulations show such mergers were common in the early universe, when clusters were packed tighter and galactic real estate was scarce, the smoking gun. M22's stars have markedly different chemical compositions between the two cores, suggesting they might have originated in distinct stellar nurseries before being forced into this awkward cosmic cohabitation. One nucleus gleams with stars rich in alpha elements like oxygen and magnesium, forged in supernova explosions, while its counterpart hosts stars laced with oddball metals like barium and europium, the telltale signatures of slower neutron capture processes in older stellar generations. But there's a problem with this tidy story. If M22 were truly a merger remnant, we'd expect to see tidal tails, streamers of stars ripped loose during the violent encounter stretching far beyond the cluster. Yet none appear in deep surveys. That's led some astronomers to propose a far stranger alternative: gravitational sleight of hand. M22 orbits close to the Milky Way's crowded center, where the pull of our galaxy's supermassive black hole could be warping spacetime enough to create a gravitational mirage. In this scenario, one core might actually be the distorted, magnified image of the other, bent around an unseen mass like light through a lens. It's a phenomenon we've seen on larger scales with galaxy clusters, but never before in something as small as a globular cluster. Yet the plot thickens when you consider M22's peculiar residence. Nestled between the twin cores lies an unusual population of millisecond pulsars, neutron stars spinning hundreds of times per second. These cosmic lighthouses typically congregate near a cluster's center where stellar densities are highest, but here they're oddly dispersed, as if avoiding some invisible boundary between the two nuclei. Even stranger, some pulsars emit radio waves that flicker erratically when passing behind the cluster's cores, as if something dense and unseen, perhaps dark matter clumps or rogue black holes, is warping their signals. The most radical explanation: we might be witnessing the aftermath of a black hole's dinner party. Intermediate mass black holes are thought to lurk in some globular clusters, and if two such objects once anchored M22's separate cores, their gravitational tug of war could have prevented a full merger. Now imagine one black hole eventually devouring the other. The resulting kick from the merger's gravitational waves could have sent the survivor careening away, leaving behind the ghostly imprint of dual cores in the stars it once governed. It's a cosmic magic trick where the magician vanishes mid-act, leaving only the illusion behind. Whatever the truth, M22's twin hearts challenge everything we thought we knew about how star clusters evolve. Are they frozen in the aftermath of a collision, caught in a gravitational hall of mirrors, or bearing scars from a black hole's feast? Until we peer deeper into this celestial riddle, one thing's certain: the universe loves a good twin mystery, especially when it defies all expectations. NGC 2173 should be the last place you'd expect a cosmic fountain of youth, a globular cluster so ancient its stars were born when the universe was barely a toddler. Yet nestled among its aging red giants and cooling white dwarfs, astronomers have spotted something impossible: stars that gleam with the vibrant blue hue of stellar adolescence. These aren't just late bloomers, they're cosmic Benjamin Buttons, appearing millions, sometimes billions of years younger than their cluster mates. It's as if time itself is running backward in this corner of the cosmos, and the mechanisms behind it could rewrite everything we know about how stars evolve. The first clues came from Hubble's sharp-eyed observations. While mapping the cluster's color and brightness, researchers noticed a peculiar group of stars lingering far above the expected main sequence. The standard track stars follow as they age. These outliers weren't just slightly off, they shone with the brilliance and temperature of stars in their prime, despite being surrounded by elderly neighbors. At first, scientists assumed they were interlopers, younger stars drifting into the cluster by chance. But spectroscopy revealed the truth. These stars share the same chemical fingerprints as the rest of NGC 2173, proving they're native to the cluster. They didn't wander in, they somehow cheated time. So how does a star turn back the clock? One leading theory hinges on stellar cannibalism. In the cluster's crowded core, binary stars orbit perilously close, and over eons, the stronger gravity of one star can siphon gas from its companion. This stolen fuel rejuvenates the thief, reigniting nuclear fusion in its core and erasing the telltale signs of aging. Picture a vampire growing younger with every sip, except here, the blood is hydrogen, and the result is a star that glows like it's half its age. Supporting this, many of NGC 2173's blue stragglers show elevated levels of helium and lithium. elements that pile up in stars that have recently gorged on fresh material. But there's a twist. Some of these time-defying stars show no evidence of a binary partner. That's led to an even wilder explanation: stellar collisions. In the cluster's dense heart, stars don't just drift peacefully, they smash together like bumper cars, their violent mergers creating Frankenstein's monsters with scrambled ages. When two middle-aged stars collide, their combined fuel reserves mix unevenly, sometimes leaving pockets of untapped hydrogen near the surface. The result: a star that looks deceptively spry, its outer layers blazing with youthful energy while its core remains ancient. Simulations show these cosmic mashups could account for at least half of NGC 2173's backward aging stars, their deceptive glow a testament to the chaos of crowded space. Yet the most tantalizing possibility pushes beyond known physics. A handful of these stars exhibit chemical anomalies that don't fit either theft or collision models, their surfaces suspiciously rich in elements like carbon and nitrogen, as if something stirred their insides like a celestial spoon. Some theorists speculate these outliers might have encountered dark matter, their cores absorbing invisible particles that alter fusion rates in unpredictable ways. It's a long shot, but if true, it would mean star clusters could be hiding natural laboratories for exotic physics, places where the ordinary rules of stellar lifespans don't apply. Whatever the cause, NGC 2173's Benjamin Button stars force us to confront a humbling truth: aging in the cosmos isn't always a one-way street. Between theft, collisions, and maybe even dark matter's hand, the universe has more tricks for rewinding time than we ever imagined. And if these processes are common, it means the night sky might be full of stellar imposters, stars that shine with borrowed youth, whispering secrets about how little we truly understand the passage of cosmic time. Globular cluster NGC 6401 hides a secret, an eerie, perfect ring of X-rays encircling its core like a cosmic halo. This isn't some artistic rendering or optical illusion. Space telescopes have captured the glow in striking detail, a shimmering loop of high-energy radiation where none should exist. Rings like this typically mark the aftermath of stellar explosions, the shockwaves of supernovas carving bubbles in space. But here's the catch: NGC 6401 shows no signs of recent supernovas, no debris clouds or pulsars left behind. So what carved this ghostly circle into the cosmos? One leading theory points to a long-forgotten cataclysm. Centuries or even millennia ago, a massive star in the cluster might have silently collapsed into a black hole, its death throes too faint for historical astronomers to record. While most supernovas explode outward in all directions, this one could have been a failed explosion. A fizzled detonation where the star's core imploded without the usual fireworks. The resulting shockwave, weaker than a typical supernova but still powerful, might have pushed outward in a near-perfect sphere, heating the surrounding gas until it glowed in X-rays. Over time, the cluster's motion through space would stretch this bubble into the ring we see today, like a celestial smoke ring frozen in time. Yet there's a problem with this tidy story. The ring is too symmetrical. Supernova remnants tend to be messy, their shockwaves warped by uneven gas densities or magnetic fields. That's led some astronomers to propose an even wilder origin, a collision between a neutron star and a white dwarf. When these ultra-dense objects spiral together, they don't just merge, they can trigger a thermonuclear firestorm on the white dwarf's surface, blowing off its outer layers in a crisp, spherical shell. The energy released would be just enough to create an X-ray ring without the full violence of a supernova, leaving behind a subtle, symmetrical scar. But the plot thickens. Recent observations reveal the ring isn't just glowing, it's pulsing, its brightness fluctuating in a slow, rhythmic pattern. That's led to a radical third idea: dark matter annihilation. If NGC 6401's core harbors a dense knot of dark matter particles, their occasional collisions could release bursts of energy, superheating the surrounding gas into a glowing ring. The pulsations might then come from the cluster's rotation, with the dark matter's distribution causing the ring to brighten and dim like a cosmic lighthouse. The implications are staggering. If this ring stems from a quiet stellar collapse, it means we've underestimated how many stars die without fanfare. If it's a neutron-star merger, it hints at a new class of cosmic explosions hiding in plain sight. And if dark matter is the culprit, it could be our first glimpse of this elusive substance shaping visible structures. For now, NGC 6401's X-ray halo remains a riddle of celestial ouroboros with no beginning, no end, and no easy explanation. Abell 1689 isn't just a star cluster, it's a cosmic funhouse mirror, warping the fabric of space so dramatically that it twists distant galaxies into surreal, elongated smears of light. This colossal gathering of galaxies, located over 2 billion light-years away, possesses gravity so immense it bends the very path of light passing through it, a phenomenon known as gravitational lensing. Normally, this effect simply magnifies background objects, giving astronomers a clearer view of the distant universe. But Abell 1689 does something stranger. It stretches and contorts these galaxies into shapes that defy logic, creating patterns so bizarre they've forced scientists to question whether we're missing a fundamental piece of physics. The first clues came from Hubble's images of the cluster, which revealed ghostly arcs of light stretched and duplicated versions of galaxies far behind it. Think of it like looking through a glass of water and seeing a straw bent at impossible angles, except here, the straw is an entire galaxy, and the glass is a trillion suns worth of invisible mass. These distortions should follow predictable patterns based on Einstein's theory of relativity, but in Abell 1689, the math keeps falling short. Some arcs are too sharp, others too elongated, as if an unseen hand is tweaking the lens. That's where the mystery deepens. To match the observed distortions, the cluster would need up to 10 times more mass than its visible galaxies and gas clouds account for. Dark matter is the obvious suspect, but here's the twist. Even when factoring in generous estimates of dark matter's distribution, the lensing effects remain off by a staggering margin. Some researchers speculate the discrepancy might hint at dark matter behaving in unexpected ways, clumping more densely near the cluster's core, or perhaps interacting with itself through forces beyond gravity. Others propose a radical alternative, that spacetime itself might be more elastic near such massive objects, warping light in ways relativity alone can't explain. But the weirdness doesn't stop there. Amid the chaos of distorted galaxies, astronomers found a few that appear too perfectly magnified, as if the cluster's lens has no optical flaws at all. This too good to be true sharpness suggests an eerie fine-tuning in the mass distribution, almost as if the dark matter is arranged in precise, invisible filaments that focus light like a cosmic telescope. It's a level of order that defies the randomness we expect from cosmic structures, raising the spine-tingling question: could there be unknown laws governing how dark matter sculpts spacetime? Whatever the answer, Abell 1689 does more than bend light. It bends our understanding of the universe. With every distorted galaxy it reveals, the cluster whispers the same unsettling truth: that gravity's rulebook might have chapters we haven't even opened yet. And until we decode its secrets, this cosmic lens will keep showing us reflections of a universe far stranger than we imagined. And you see, 121 shouldn't be this rebellious, not for a globular cluster that spent nearly 12 billion years orbiting our galaxy. Every rulebook says it should be drowning in dark matter, its motion dictated by the invisible gravitational glue that holds galaxies together. Yet this ancient cluster moves with a strange, unburdened grace, speeding through space as if it somehow slipped free of dark matter's grasp. It's not just defying expectations, it's throwing the entire cosmic rulebook into question. The anomaly first caught scientists' attention when precise velocity measurements revealed NGC 121 was zipping along its galactic orbit too fast, almost as if it were lighter than it should be. Dark matter models predict clusters like this should be slowed by the drag of invisible halos, their paths curbed by the extra weight. Instead, NGC 121 races ahead like a cyclist who's ditched their backpack, leaving theorists scrambling to explain how it's cheating physics. Some argue the cluster might have shed its dark matter cloak long ago, stripped bare by tidal forces as it plunged through the Milky Way's densest regions. Picture a ship losing cargo in a storm, except here, the cargo is an invisible substance we can't even see. But here's the twist: tidal stripping shouldn't work this efficiently. Simulations show dark matter halos cling stubbornly to globular clusters, resisting removal even under brutal gravitational abuse. That's led a growing faction of researchers to consider something far more radical. What if dark matter isn't the culprit at all? Enter modified Newtonian dynamics, or MUND, a controversial theory suggesting gravity behaves differently on cosmic scales than Einstein predicted. In this framework, NGC 121 speed isn't an anomaly. It's the expected outcome when you ditch dark matter entirely and tweak gravity's equations instead. Supporting this idea, the cluster isn't alone in its rebellion. A handful of other globulars show similarly suspiciously speedy orbits, all moving like they've shaken off unseen anchors. If MUND is correct, these cosmic speedsters aren't exceptions. They're the rule, revealing flaws in our reliance on dark matter as a catch-all explanation. Yet skeptics counter with their own smoking gun. Galaxies rotating too fast for visible matter alone, their outer stars whirling as if gripped by invisible hands. How can one explain those while dismissing dark matter's role here? The debate rages, but NGC 121 holds one more clue deep in its stellar chemistry. Unlike most globulars, its stars show oddly uniform metal content, suggesting it formed in an environment where dark matter's gravitational stirring didn't mix the cosmic pot as violently as expected. It's a subtle detail, but for theorists, it's fuel for the fire, proof that this cluster's entire history might be a roadmap to an alternate understanding of gravity itself. Whether it's a dark matter defector or a signpost to new physics, NGC 121 forces a humbling realization. After decades of mapping the cosmos, we still don't fully understand the invisible scaffolding holding it together. And until we do, every rebellious cluster like this one is a reminder that the universe's greatest mysteries often lurk in the gaps between our theories and their cracks. Deep in the constellation of Pisces, astronomers have stumbled upon something that shouldn't exist, a ghostly smudge of light with no stars to call its own. Dubbed the starless cluster candidate, this enigmatic patch of sky defies classification. At first glance, it resembles a globular cluster, one of those ancient, tightly packed stellar cities we've come to recognize. But peer closer and the truth becomes unsettling. There's not a single star visible within it, just a faint, diffuse glow hovering in the void like a cosmic afterimage. The question isn't just what it is, it's whether we're looking at a cluster that's lost its stars or something entirely new, a celestial phantom that's never been seen before. The debate hinges on two possibilities, each more intriguing than the last. On one side, the dark cluster theory suggests this could be the skeletal remains of a star group whose members have been stripped away. Imagine a globular cluster venturing too close to the Milky Way's gravitational tides, its stars plucked one by one like grapes from a vine, until only the faintest trace of their collective gravity lingers. Supporters point to the object's subtle gravitational lensing effect, bending the light of background galaxies in a way that hints at concentrated mass. If true, it would mean we've found the universe's first documented ghost town, a place where stars once thrived, but now only their invisible bonds remain. Yet there's a catch: the glow. Unlike dark matter halos, which are entirely invisible, this object emits a faint, uniform light. That's led to a wilder idea. Perhaps it's not a cluster at all, but a rogue nebula, a vast cloud of ionized gas hurtling through intergalactic space, lit from within by some unseen energy source. Spectroscopic analysis reveals traces of hydrogen and helium, but none of the heavier elements typically forged in stars. It's as if this cloud is primordial, a relic from the universe's infancy that somehow avoided stellar pollution for billions of years. If confirmed, it would be the first of its kind, a pristine pocket of ancient gas untouched by star formation. Then there's the third, most speculative option, a dark matter experiment gone cosmic. Certain theories predict that dark matter particles, when densely packed, could interact in ways that produce faint radiation. Could this smudge be the first visible signature of dark matter's hidden physics? The notion isn't as far-fetched as it sounds. In labs on Earth, scientists hunt for dark matter's whispers using ultra-sensitive detectors. Out there, nature might have built its own detector on a galactic scale. For now, the starless cluster candidate remains a riddle wrapped in a haze. Whether it's a graveyard, a fossil, or something entirely unprecedented, one thing is clear: it's forcing us to rewrite the definitions we thought were set in stone. And in a universe that thrives on surprise, that might just be the most thrilling discovery of all. Fast radio bursts have long been one of space's most tantalizing puzzles. Brief, brilliant blasts of radio waves that flare for just milliseconds before vanishing without a trace. But when astronomers traced one particular repeating burst, FRB 201800916b, back to its origin, they got the shock of their careers. It was coming from a star cluster. Not just any star cluster, but an ancient globular group orbiting a distant galaxy. The discovery sent shockwaves through the astrophysics community because globular clusters are the last place you'd expect these energetic eruptions. They're retirement homes for elderly stars, quiet neighborhoods where stellar violence should be a thing of the past. Yet here was this cosmic repeater, firing off crisp, powerful signals like a lighthouse in a graveyard. The implications are staggering. Fast radio bursts pack more energy in a millisecond than our sun emits in weeks, and most theories tied them to cataclysmic, one-time events, collapsing neutron stars, evaporating black holes, or other blink-and-you'll-miss-it disasters. A repeating source changes everything. It points to something that can produce these bursts again and again, something lurking in an environment where nothing should have that kind of power. One leading suspect, a highly magnetized neutron star called a magnetar. These spinning stellar corpses have magnetic fields 1 trillion times stronger than Earth's, capable of twisting spacetime itself. When their crusts crack under magnetic stress, they could theoretically unleash the precise mix of energy and precision we see in repeating FRBs. But here's where the star cluster location throws a wrench in the works. Magnetars typically form from young, massive stars, the kind that burn out fast and die spectacularly. Ancient globular clusters shouldn't have any left. That's led to wilder theories, like collisions between ultra-dense white dwarfs or neutron stars, events so rare they'd explain why we've only spotted one such FRB source in a cluster. Then there's the extraterrestrial angle, not little green men, but a more subtle possibility. Advanced civilizations might use tightly focused radio beams for propulsion, communication, or even interstellar art projects. While there's zero direct evidence for this, the precision of some bursts does raise eyebrows. Perhaps the most compelling clue lies in the signal structure. This particular FRB isn't just repeating, it's cycling through distinct modes, switching between high-frequency and low-frequency bursts in a pattern that defies natural explanations. It's as if we're listening to a cosmic dial twisting between stations, a behavior unheard of in known astrophysical objects. Some researchers suggest this could be evidence of a magnetar orbiting another dense object, their gravitational dance modulating the bursts like a celestial conductor. Others propose a radical alternative, quantum phenomena in neutron star atmospheres, where bizarre physics generates these structured outbursts. What makes this discovery truly paradigm-shifting is the cluster environment itself. The crowded stellar neighborhood means whatever's producing these bursts has survived billions of years in a gravitational mosh pit, dodging collisions and tidal forces that should have destroyed it. That longevity hints at something fundamentally new, a stellar remnant tougher, stranger, or more exotic than anything in our current playbook. Every time this distant repeater fires, it's not just sending energy across the cosmos. It's challenging us to rethink what's possible in the universe's oldest stellar communities, and that's a signal worth listening to. Globular cluster M5 should be a serene retirement community for aging stars, a place where ancient suns drift through their golden years in quiet predictability. But peer deeper, and this cosmic elder reveals a ferocious secret. It crackles with a magnetic field so intense, so meticulously structured. It's as if the cluster has an invisible nervous system threading through its core. Unlike the chaotic, tangled fields seen in most globulars, M5's magnetism forms vast, sweeping arcs, orderly rivers of force that defy the usual rules of stellar senescence. This isn't just a magnetic field, it's a cosmic masterpiece, and its existence throws a wrench into everything we thought we knew about how clusters evolve. The first clues surfaced when radio telescopes detected strange, polarized emissions humming from M5's heart. These weren't the random static of stellar collisions or pulsar winds, but a coherent signal, as if the cluster itself were broadcasting on a magnetic frequency. Further observations revealed the true scope. M5's field stretches across dozens of light years, its lines of force aligned like the grooves in a vinyl record. For context, most globular clusters have weak, scrambled magnetism, leftovers from primordial gas clouds or the fading ripples of long-dead stars. But M5's field is organized, a relic of some forgotten event that imprinted order onto the chaos. So what twisted this cluster into a cosmic bar magnet? One theory points to a forgotten era of stellar violence. Millennia ago, M5 might have hosted a swarm of massive, fast-spinning stars, celestial dynamos that churned out magnetic fields as they burned. When these titans died in supernovas, their explosive deaths could have woven their combined magnetism into the cluster's fabric, like blacksmiths hammering molten steel into shape. Supporting this, M5's core still harbors an unusual number of millisecond pulsars, neutron stars spinning at dizzying speeds, their intense magnetic footprints possibly reinforcing the larger structure. But there's a wilder possibility: dark matter's invisible hand. Some simulations suggest that if M5's dark matter halo, assuming it has one, interacts weakly with itself, its particles could generate large-scale magnetic fields as they drift. Picture a ghostly weather system where dark matter, winds, sculpt invisible currents into the cluster's plasma. It's a long shot, but if true, M5 could be offering us a backdoor glimpse into dark matter's secret physics. The most tantalizing clue, though, lies in the field's stability. Magnetic fields this coherent shouldn't last billions of years. They ought to decay, their energy dissipating into the void. Yet M5's endures pristine as the day it formed. That's led to a radical idea: the cluster might be alive, electromagnetically speaking. Its dense core of interacting stars could act like a self-sustaining dynamo, with close encounters between binaries and pulsars constantly replenishing the field's energy. Think of it as a cosmic perpetual motion machine, where gravity's dance fuels an eternal magnetic heartbeat. Whatever the source, M5's magnetic personality forces a reckoning. If orderly fields can persist in ancient clusters, it means these stellar cities might be far more electromagnetically active than we dreamed. Suddenly, the quietest corners of the cosmos hum with invisible energy, and M5 is just the first conductor we've noticed in the cosmic orchestra. NGC 6541 is home to a cosmic chorus unlike anything else in the known universe. At first glance, this ancient globular cluster seems ordinary, a dense ball of aging stars orbiting the Milky Way's outskirts. But when astronomers trained sensitive light-measuring instruments on its core, they detected something eerie: dozens of stars pulsating in perfect synchrony, their brightness rising and falling together like a perfectly timed light show. The odds of this happening by chance are astronomically low. These stars aren't just neighbors, they're acting as if strung together by invisible strings, and the implications could rewrite our understanding of how star clusters function. The phenomenon, called synchronized stellar variability, was first noticed when light curves revealed an uncanny pattern. Red giants, blue stragglers, and even faint white dwarfs. Stars of different sizes, ages, and compositions, all flickered in lockstep, their rhythms matching down to minute fluctuations. It's as if the entire cluster is breathing as one. Traditional astrophysics can't explain this. Stars pulse due to internal processes: helium fusion, instability in red giants, surface vibrations in younger stars, but these mechanisms are independent. There's no known way for separate stars to coordinate their heartbeats across light years of space, unless something far stranger is at play. One theory points to gravitational resonance. Imagine a room full of pendulum clocks. Over time, their swings sync up due to subtle vibrations passing through the floor. In NGC 6541, the cluster's densely packed core might act as that floor, with gravitational waves from orbiting neutron stars or black holes nudging stars into alignment. Simulations show that if a mid-mass black hole lurks unseen in the cluster's heart, its rhythmic tug could orchestrate the pulsations like a cosmic metronome. Supporting this, the synchronized stars all orbit at similar distances from the core, as if trapped in a shared gravitational groove. Yet there's a wilder possibility: magnetic entanglement. Some globular clusters harbor vast, structured magnetic fields, and if NGC 6541's is particularly strong, it could link stars like wires in a circuit. When one star's magnetic field fluctuates, say, due to a flare or internal upheaval, the change might ripple through the collective field, triggering others to follow suit. It's a stretch, but not impossible. We see hints of this in younger star-forming regions, where magnetic bridges channel energy between newborn stars. If confirmed in an ancient cluster, it would mean magnetism plays a far greater role in stellar dynamics than we ever imagined. Then there's the dark horse explanation: external forcing. NGC 6541 orbits through a region of the Milky Way thick with dark matter substructures. If the cluster periodically plows through a dense knot of this shadowy material, the gravitational jolt could send shockwaves through its stars, setting off coordinated pulsations like a drumbeat echoing through the ranks. It's speculative but tantalizing, a potential way to indirectly see dark matter's hidden architecture. Whatever the cause, this synchronized dance forces a radical rethink. If stars can communicate their rhythms across vast distances, it means globular clusters aren't just random collections of suns, they're interconnected systems, with hidden mechanisms binding them together. Suddenly, the universe feels less like a scattering of isolated objects and more like a vast humming network, where even the oldest stars might still be whispering to one another. Omega Centauri has always been the heavyweight champion of star clusters, a behemoth so massive it blurs the line between cluster and galaxy. With nearly 10 million stars packed into a sphere just 150 light-years wide, it outshines every other globular cluster in the Milky Way by a staggering margin. But here's the twist: when astronomers tried to weigh it, the numbers didn't add up. Omega Centauri isn't just big, it's impossibly heavy, tipping the scales at something like 5 million solar masses. That's not just unusual, it's a cosmic anomaly screaming for an explanation, and the leading theory is as dramatic as it gets. This isn't a star cluster at all. It's the cannibalized heart of a long-dead galaxy, a relic from a time when the Milky Way was still stitching itself together from the bones of its neighbors. The first clue lies in its stars. Unlike typical globular clusters, where stars are born from the same primordial gas cloud and share nearly identical chemical fingerprints, Omega Centauri's stellar population is wildly diverse. Some stars are rich in heavy elements like iron and oxygen, while others are almost pristine, barely touched by the nuclear furnaces of later generations. This isn't the uniform chemistry of a single collapse event. It's the messy signature of a system that formed over eons, building itself up in layers like a cosmic onion. Even stranger, the stars orbit in multiple, distinct streams, as if they're still remembering the chaotic dances of their original galactic home. Then there's the dark matter problem. Normal globular clusters don't have dark matter halos. Their gravity comes entirely from visible stars, but Omega Centauri's motion hints at something unseen lurking in its depths. When researchers tracked the velocities of its outer stars, they found them moving too fast for the cluster's visible mass to hold them, the only explanation. An invisible gravitational anchor, something like the dark matter skeleton of a dwarf galaxy. If true, it means Omega Centauri isn't just wearing a dead galaxy's stars like a trophy, it's still carrying its ghost. The smoking gun might be hiding in the cluster's core. Hubble's sharp eyes revealed a dense, bright nucleus, exactly where you'd expect the supermassive black hole of a dwarf galaxy to reside. Most globular clusters don't have central black holes, but galaxies do, and if Omega Centauri's heart holds even a fraction of the mass it should, it would explain why this cluster behaves more like a galactic bully than a quiet stellar retirement home. Some simulations suggest the Milky Way's gravity could have stripped away Omega Centauri's outer stars over billions of years, leaving only its core behind, a cosmic decapitation preserved in starry amber. The implications are staggering. If Omega Centauri is really the corpse of a galaxy, it means the Milky Way's violent past is written in its stars. Other so-called globular clusters might be hiding similar origins, their true identities masked by time and tidal forces. Worse, it challenges how we define these cosmic categories in the first place. What's the difference between a big cluster and a small galaxy? The answer might not be size or shape, but memory, the lingering traces of a history too violent to forget. For now, Omega Centauri remains the universe's most imposing riddle, a reminder that even the brightest things in the sky can be shadows of something far older, far stranger, and far darker than we ever imagined. Globular cluster M30 should be a graveyard of aging stars, its members quietly cooling into retirement after billions of years of steady burning. But nestled among its crimson giants and fading dwarfs, astronomers have spotted cosmic rule-breakers, vibrant blue stars shining with the vigor of youth. These so-called blue stragglers glow hotter, brighter, and bluer than their peers, like finding a group of 30-year-olds at a nursing home party. Their existence defies everything we know about stellar evolution, and the secrets behind their rebellious energy could rewrite the textbooks on how stars cheat time. The leading theory, stellar vampirism. In M30's densely packed core, binary stars orbit dangerously close, so close that the stronger gravity of one star can siphon hydrogen fuel from its companion. This stolen gas reignites nuclear fusion in the thief's core, essentially hitting the reset button on its lifespan. Picture a cosmic fountain of youth where one star grows younger by draining the lifeblood of another. Evidence for this comes from spectroscopic studies revealing elevated levels of helium and carbon in many blue stragglers, telltale signs of recent feasting on fresh hydrogen. Some even show traces of lithium, an element normally destroyed early in a star's life, proof that their surfaces have been chemically rejuvenated by stolen material. But there's a darker, more violent alternative: stellar collisions. In M30's crowded core, stars don't just drift, they crash. When two middle-aged stars collide, their merged cores mix unevenly, creating a Frankenstein's monster with a scrambled interior. Hydrogen that would have taken billions of years to reach the core suddenly finds itself in the furnace, igniting a burst of fresh nuclear fusion. The result: a star that shines with deceptive youth, its outer layers blazing blue while its ancient heart remains hidden. Computer simulations show these cosmic pileups could account for up to half of all blue stragglers, their vibrant glow masking a turbulent origin story. The most compelling evidence for this comes from their oddball rotations. Normally, stars slow down as they age, like spinning tops losing momentum. But many blue stragglers whirl at breakneck speeds, some completing a full rotation in just hours, a clear fingerprint of the angular momentum injected during a violent merger. Others exhibit strange chemical bruises, surface patches rich in elements like nitrogen that suggest their outer layers were churned up during impact, like mud stirred from the bottom of a pond. Yet the real mystery lies in their distribution. Unlike most globular clusters where blue stragglers concentrate in the core, M30's rebels are scattered outward as if something or someone kicked them to the edges. This has led to a wildcard theory: dark matter interference. If M30 harbors an unseen dark matter subhalo, its gravity could be perturbing stellar orbits, herding collision-borne stragglers into unexpected orbits. It's a long shot, but if true, it would mean these stars aren't just defying stellar evolution, they're dancing to the tune of invisible forces we're only beginning to map. Whether through theft, violence, or shadowy intervention, M30's blue stragglers prove that even in the oldest corners of the cosmos, the rules are made to be broken. And as we unravel their secrets, we're not just learning about stars, we're discovering the universe's hidden playbook for rewriting time itself. Palomar 12 isn't just a star cluster, it's a cosmic crime scene, its stars stretching across the sky like breadcrumbs left by a gravitational thief. Unlike most globular clusters, which huddle in tight spherical formations, Palomar 12 trails a spectacular stream of stars over 30,000 light-years long, a shimmering ribbon unraveling into the Milky Way's halo. This isn't accidental. It's the aftermath of a slow-motion heist, our galaxy's gravity methodically stealing stars from the cluster's outskirts, one stellar theft at a time. The evidence is written in the trajectories of these exiled stars. Precise measurements from the Gaia Space Observatory reveal they move in perfect lockstep with Palomar 12's core, tracing the same orbital path like celestial prisoners dragged in chains. Their chemical fingerprints match the cluster's two higher ratios of elements like iron and magnesium than typical Milky Way stars, a dead giveaway that they were forged in the same stellar nursery billions of years ago. Normally, clusters lose stars haphazardly, their escapees scattering like dropped marbles, but Palomar 12's stream is surgically precise, a testament to the Milky Way's patient, relentless pull. What makes this cluster's fate even stranger is its origin story. Palomar 12 didn't start life in our galaxy at all. Spectroscopy shows its stars are younger and more metal-rich than most globular clusters, suggesting it was born in the Sagittarius dwarf galaxy, a tiny neighbor the Milky Way is currently devouring. Roughly 1.7 billion years ago, our galaxy's gravity likely plucked Palomar 12 from Sagittarius like a fruit from a tree, sending it careening into orbit around us. The cluster's elongated path still carries echoes of that ancient abduction, swinging too close to the Milky Way's disk every few 100 million years. Each pass strips away more stars, elongating the stream further. Here's where the plot twists. Palomar 12's tail shouldn't be this coherent. Simulations predict tidal streams from disrupted clusters ought to fray over time, their stars scattering as they interact with dark matter subhalos or spiral arms. Yet this stream remains razor-sharp, its edges as defined as if drawn with a cosmic ruler. Some theorists propose an invisible culprit: dark matter filaments. These thread-like structures, remnants of the universe's large-scale web, might act as stellar highways, channeling the stream's stars along precise routes. Others suggest the cluster's initial spin could be the key. Unlike most globulars, which rotate slowly, Palomar 12 whirls fast enough that centrifugal force might be helping slingshot stars outward in an orderly line, like sparks flying from a spinning grindstone. The real treasure lies in what this stream reveals about our galaxy's hidden architecture. By mapping the tail's curvature, astronomers have detected subtle kinks, places where the Milky Way's gravity has yanked the stream off course. These betray the presence of unseen mass, perhaps a rogue cloud of gas, a clump of dark matter, or even a small black hole drifting unseen through the galactic suburbs. Every bend in Palomar 12's tail is a clue, a breadcrumb leading us closer to mapping the invisible scaffolding shaping our corner of the cosmos. For now, this dying cluster keeps spinning out its stellar thread, a silent witness to the Milky Way's appetite for destruction. But its fate is sealed. In another few billion years, Palomar 12's core will dissolve entirely, its stars scattered across our galaxy's halo. Only the stream will remain, a ghostly scar on the sky, marking where a cluster once fought gravity's inexorable pull and lost. At the heart of Globular Cluster M4, astronomers have uncovered a cosmic contradiction, a neutron star and white dwarf locked in a gravitational embrace so tight they shouldn't exist. This binary system, dubbed PSRB 1600-2026, whirls around each other every 191 days, separated by a distance that defies all predictions. Normally, pairs this close would have merged billions of years ago, consumed by the neutron star's monstrous gravity. Yet here they are, dancing on the edge of annihilation like a cosmic tightrope act, forcing scientists to question whether we've misunderstood the fundamental rules of stellar relationships. The neutron star, a pulsar spinning at 100 revolutions per second, should have long since shredded its companion. Born from a supernova that ought to have blasted the white dwarf away, this system survived against impossible odds. Even stranger, the white dwarf is far too massive for conventional models, weighing in at roughly half the Sun's mass when it should have been whittled down to a fraction of that by stellar winds. It's as if the universe left these two objects in a state that breaks every equation in the astrophysics playbook. One radical theory suggests they cheated death through a celestial bait and switch. Billions of years ago, the pulsar might have had a different partner, a massive star that later exploded, kicking the system into a chaotic orbit. The surviving neutron star could have then captured the current white dwarf during a close encounter in M4's crowded core, a gravitational hijacking that reset the binary's lifespan. Supporting this, the system's orbital plane is tilted unusually, a fingerprint of past violent interactions. But here's the twist: simulations show even a captured white dwarf shouldn't have stabilized in such a tight orbit. That's led to wilder ideas like dark matter intervention. If an unseen halo of dark matter envelops M4, its extra gravity might have subtly altered the binary's decay rate, acting as an invisible buffer against merger. Or perhaps the pulsar's intense magnetic field interacts with the white dwarf's ionized atmosphere, creating a repulsive force that counteracts their inward spiral. The implications stretch far beyond this odd couple. If such binaries can persist, it means the universe might be hiding entire populations of impossible system-stellar partnerships that refuse to follow the rules. And if dark matter or magnetism is the secret glue holding them together, every one of these outliers could be a clue to forces we've yet to discover. For now, PSRB 1600-2026 keeps spinning its tale of defiance, a cosmic rebel rewriting the laws of engagement one orbit at a time. From vanishing star clusters to cosmic diamonds older than time itself, we've journeyed through 30 of the most mind-bending discoveries that prove the universe is far stranger than we ever imagined. These aren't just curiosities, they're cosmic game changers, rewriting the rules of stellar evolution, dark matter, and even time itself. Phantom clusters that flicker in and out of existence, rogue planets drifting like cosmic orphans, black hole factories churning out gravitational monsters. Every revelation forces us to question what we thought we knew. And perhaps the most thrilling part, this is just the beginning. For every mystery solved, a dozen more emerge, reminding us that the cosmos thrives on the unexpected. Take Omega Centauri, a star cluster so massive it might be the corpse of an ancient galaxy, or Paloma 12, unraveling into a stellar stream as the Milky Way devours it bite by bite. Even the quietest corners of space hide violent neutron stars locked in impossible orbits, magnetars humming electric lullabies, and dark matter sculpting unseen rivers through the void. These discoveries don't just push boundaries, they smash through them, revealing a universe that's wilder, more dynamic, and more mysterious than our textbooks ever dared suggest. Now it's your turn. Which of these cosmic oddballs left you spellbound? Was it the singing stars of Messier 80, their radio pulses echoing like a celestial symphony? Or the rebellious blue stragglers in M30, cheating death through stellar theft and collisions? Drop your favorites in the comments and let's geek out over the universe's most jaw-dropping enigmas together. And if you're hungry for more mysteries, from rogue black holes to galaxies that defy physics, hit subscribe and ring the bell. The cosmos has endless secrets waiting to be uncovered, and we're just getting started. Until next time, keep looking up, because out there, anything is possible.